Hello, hello. Is the screen visible?
Yes, sir.
Okay, thank you. Uh, Good afternoon, everybody, and welcome to the course on principles and practices of process equipment and plant design. I am here to solve week 8 NPTEL previous year assignment questions. I am Suraj P from Chemical Engineering Department, IIT Kharagpur. So, let's see the first question. Which of the following is incorrect guidelines about routing of fluids in shell and tube heat exchanger? First one is corrosive liquids are preferably routed through tubes. Second, liquid at high temperature is generally routed through the tube side. Option C, fluids at higher operating pressure is generally routed through the shell side. High viscous liquids are generally routed through the shell side. So, uh, can you tell what will be the answer for this preferred routing, which is incorrectly written here?
D option.
Option D. Uh,
Yes.
Actually, the correct answer is option C, because uh, like high pressure is usually preferred in tube side, and high viscous is can be routed through shell side. High viscous fluids can be routed through shell side. There are some guidelines for allocation of fluids in the shell and tube heat exchanger. Like first one, it depends on the heat transfer coefficient of the fluid. Like generally the heat transfer coefficient is a function of the properties of the fluid and the flow rate of the fluid. When the uh, flow rate of one fluid is a lower one compared to other, uh, allocating in shell side will allow higher, uh, will will allow to get higher heat transfer coefficient. So generally fluids with lower heat transfer coefficient is allocated in shell side. So uh, lower heat transfer coefficient can be obtained by the fluid with lower flow rate. So the fluid with lower flow rate will be generally having low heat transfer coefficient, and they are routed through shell side. And the second one is fouling. uh, Fouling inside the tubes are easier to clean when compared to shell side. Fluids which have greater tendency to foul are allocated in tube side. uh, and you were telling that when the viscosity increases, the fouling increase, like you were telling that thing, na? Hello.
Sorry, sir.
Huh. Like when viscosity increases, the fouling increase, like you were telling about that concept. uh,
Yes, sir. Yes.
uh, but but instead of pump fouling, to prevent fouling in shell side, we can use a higher flow rate. Higher fluid velocity can reduce the fouling in the shell side. So uh, this is not a general term, generalized case. So if we pass high viscous fluid at high velocity through the shell side, then fouling can be prevented. And fluid with great tendency to foul will be often having lower heat transfer coefficient, uh, and they are routed through the shell side. Then material of construction, like expensive material of construction are preferred in the tube side. Like expensive tubes are when compared to shell, expensive material are preferred in the tube side. Expensive material of construction, like if the fluid is that we are handling is corrosive and uh, fluid have high temperature, then the uh, material of construction in the tube side should be compatible. So uh, so expensive material are preferred in the uh, expensive material of construction of the tubes are preferred when compared to shell. Then this will decrease the total overall expensive cost. Then operating pressure, like stream with higher pressure is allocated in the tube side, but here the option they have written is fluid with higher operating pressure is routed through the shell side. This is because uh, stream with higher pressure is preferred in tube side, because smaller diameter of tube, uh, thinner the wall is required for the same pressure which is handled. So for a smaller tube, thinner the wall is required for same pressure which is handled, and so tubes are more effective at containing the high pressure than shell side. Then next one is the pressure drop. Pressure drop across the tube. For same pressure drop, higher heat transfer coefficient will be obtained on the tube side than the shell side. So fluids with lower allowable pressure drop is normally allocated in the tube side. Then next one is the viscosity. Higher heat transfer coefficient will be obtained by allocating more viscous material on the shell side. So more viscous liquids are preferred in the shell side of the tube. So option D is actually correct. So the correct answer for this question is option C. The statement of option D is correct, because high viscosity means higher heat transfer coefficient. So higher heat transfer coefficient can be obtained in the shell side, but the flow should be turbulent in nature. Then fluid temperature. Uh, Passing hotter fluid in the tube side will reduce the contact with the shell surface and the environment. This will minimize the heat loss. Also it will increase the safety of the heat exchanger. The next one, so the correct answer for this question is option C. Here the correct answer is fluid at high operating pressure is routed through the tube side. Question number 2, for linear operating and equilibrium line, extraction factor in liquid extraction is defined as option A, slope of operating line by slope of equilibrium line. Option B, slope of equilibrium line to slope of operating line. Option C, slope of equilibrium line into operating line. Option D, none of the above. What is the extraction factor? Like similar to absorption, in absorption also we have absorption factor.
Sorry, sir.
Option C. Uh, actually, the
Oh,
actually the answer is option B. slope of equilibrium line to slope of operating line. So let us consider a counter current extractor where the feed is entering the first extractor and the solvent is entering in end stage of extractor, then and we have obtained the extract as E, the which combustion is XE out, and the raffinate is leaving at XR out. Let the molar flow rate of feed solvent be F and that of extract solvent be S, extraction solvent be S, then we should assume that the system is immiscible, that the solvent that two layers are formed after the extraction phase. So on, and also we are assuming that the this stream velocity is same, that is F equal to R. Whatever feed is entering, that molar flow rate will be equal to molar flow rate of raffinate. Similarly, S equal to E. Then performing the material balance around this section, we will get F into XF plus S into XE equal to F into XR plus E into X out. So this is the operating line equation for extraction. Similarly, from experimental, after doing experiment, we will get equilibrium line equation for extraction. So on plotting the mole fraction of extract versus raffinate on the y-axis on solute free basis, the operating line line will be a straight line. So here we have the extraction factor given by epsilon, which is slope of equilibrium to slope of operating line. Let the slope of equilibrium line be K, then slope of operating line, which is F by S. So extraction factor is slope of equilibrium by operating line. So the correct answer for this question will be option B. Then question number 3, tie line connects the composition of two faces dash when the process of extraction is presented in a rectangular plot. The tie line that passes through feed point is used to estimate the dash amount of solvent required. Options are option A, entering a tray and minimum solvent required. Option B, in equilibrium, maximum solvent required. Option C, entering a tray, maximum solvent required. Option D, in equilibrium, minimum solvent required. So tie lines connect the composition of two faces in
Equilibrium.
yes, tie line connects the faces in equilibrium. Then for a rectangular plot, if the tie line is passed through the feed point to the up to the point where it meets the solvent, then solvent and raffinate, then we will obtain a minimum or maximum amount of solvent required. Like from
Minimum. D option.
yes, so the answer will be D, option D. So here we have the tie line, which is the here we have three. This is the ternary plot, or also called as rectangular plot for extraction. Here we have the solvent, solute, and this is the carrier. This is the solvent for the solute. This is extraction solvent, and this is the carrier solvent. Carrier solvent for solute. This is the equilibrium curve for this ternary system. So a line joining the this is the extract section and this is the raffinate section. A line joining the extract section and raffinate section will join at plate point, and only separation is possible inside this dome area. So outside this area no separation is possible, and these parallel lines are the operating line which is obtained by material balance solving. So here they have shown the feed point as F. So if we need to find a mixture composition, if we mix the solvent S with feed F, which is at 75%, then we can join the point S and F and do the balance, like S in kilomole per hour equal to this composition into F plus S. So from there we will get the mixture point XM. Then we can mark the point M. Then we can draw a line parallel from this point, that is extract point and raffinate point, passing through the mixture point, obtained by solving this S plus F into X mixture equal to solvent flow rate S. So this line joining the extract point and raffinate point, which passes through the mixture point, is drawn. Then from here we can find the delta min by joining these 2 points, like F and S can be extended to the outside of the triangle. Similarly, this R and E can be extended to the outside of the triangle. From there we will get the delta min, which is called as the minimum difference point. From there we can obtain the minimum solvent required for extraction. So the answer for question number 3 is D, option D. So next question number 4, choose the correct option among the following. Two statements are given. Statement 1, the purpose of providing fins on heat transfer surface is to increase the effective heat transfer area. Then indirect contact heat exchangers are preferred over direct contact heat exchangers to avoid contamination of streams involved in heat transfer. Then option A, only statement 1 is true. Option B is only statement 2 is true. Option C, both the statements are false. Then option D, both the statements are true. So what will be the answer for this? The fins are provided to
Statement 1 is correct, sir.
Statement 1 is correct. Then statement 2, like indirect contact heat exchangers are preferred over direct contact heat exchanger to avoid contamination of streams involved in heat transfer. So whether that is correct or
Yes, correct.
okay. So both the statements are true. So this is the figure of fins, which is the extended surface. So the fins provide a greater surface area. So the overall external heat transfer coefficient can be enhanced by using these type of extended surfaces. this increase the rate of heat transfer per unit length of the tube. Like if we use a fin, whether it will help to decrease or increase the total uh, if we fit a fin into the heat exchanger, then the heat exchanger becomes smaller or larger. Uh, if the main purpose of adding fin is to decrease the to make the exchanger smaller and cheaper than the corresponding plain type of tube exchanger. So if we fit these fins, then the total length required might be smaller, because the rate of heat transfer will increase per unit length. And this type of structures can be uh, impregnated on the tubes, on the external surface of the tube, or also in the internal surface of the tube, by two methods, like integrally formed tubes, like it is done by cold forming technique. Like the integrally formed tube can be used to create the fins in the inner as well as the outer side of the tube. And another technique is non-integrally formed fins, which can which is a technique which is used obtained by just attaching a piece of metal at the outside of the tube. So the non-integrally formed fins is obtained by attaching metal pieces on the outer surface of the tube. So question number 5, for estimation of heat transfer coefficient H during forced convection, Nusselt number is generally expressed as dash, and it is a function of dash. So here the symbols are: H is the heat transfer coefficient, Cp is thermal conductivity, K is thermal conductivity, Cp is heat capacity, then the PR and RE are the Prandtl number and Reynolds number, and mu is the kinematic viscosity. So what will be the formula for Nusselt number?
Option B.
Option B. Option B.
Yes, sir.
Option B and C both have the same thing, like equation for Nusselt number HD by K, but the function, how the Nusselt number is related to a Reynolds number and Prandtl number, whether it's a function of only Reynolds number, or is it a function of both Prandtl number and Reynolds number. Actually the Nusselt number is a function of both Prandtl number and Reynolds number. Like some correlations are there, like Cedar-Tate correlation, where we can calculate the Nusselt number for flow in tubes, where the Nusselt number is given as a function of Prandtl number and Reynolds number. So the correct answer is C, option C. Then when can we neglect the Cedar-Tate correlation factor in the design of tubular heat exchanger? When temperature at tube wall is not very different from bulk fluid temperature, when a low viscosity liquid flows through the tube and its viscosity is not much affected by the temperature. Option C, both A and B. Option D, none of the above.
Option C, both A and B.
Option C, both A and B. So, so the s- we can neglect the Cedar-Tate uh, correlation. Like the Cedar-Tate factor will be important only when the temperature in the wall is very much far from the bulk fluid temperature. So here option A, when the temperature of wall is not very different from bulk temperature. So in this case we can neglect the Cedar-Tate factor. Also, when the in when the viscosity of the liquid is when the high viscosity liquid flows through the tube and the viscosity is affected by the temperature, then also we need to consider the Cedar-Tate factor. But here the statement is that when a low viscosity liquid flows through the tube and viscosity is not much affected by temperature. So in both these cases we can neglect the correction factor in tubular heat exchanger. So the answer will be option C. Then question number 7. During design of a double pipe heat exchanger, if the calculated pressure drop is greater than allowable limit, the designer can either select large diameter pipe, opt for smaller diameter pipe, place fluid with high volumetric flow rate on the side with high cross sectional area, place fluid with low volumetric flow rate on the side with high cross sectional area. So choose the correct option from the following.
Option A
Option A
or
is partially correct. Like one is correct.
uh, place fluid with a lower volumetric flow rate. Option 4.
Yes. Option B is the correct answer. Like here, like if we got the pressure drop calculated greater than the allowable pressure drop, we can either place the fluid with higher volumetric flow rate. We can either route the higher volumetric flow rate through the shell side with higher cross sectional area, or we can use a larger diameter pipe. In both the cases the fluid velocity decrease, so there will be a decrease in the pressure drop, so the calculated pressure drop will come it can be reduced. Actually the calculated pressure drop should might be equal to allowable pressure drop. So in order to make it closer, we can either increase the diameter of the tube or place the fluid with higher volumetric flow rate to the side with higher cross sectional area. So in both these cases, when the diameter is increased, the fluid velocity decrease, thereby a pressure drop can be decreased. Also by placing the fluid with higher volumetric right through the tube with higher cross-sectional area, the pressure drop can be decreased. So 1 and 3 are correct answer. So option B is the correct answer. Then next one, consider the following statement. Hairpin arrangement in a double pipe heat exchanger can accommodate a larger heat exchanger length within limited floor space. For same inlet and outlet temperature of hot and cold fluids, delta T LMTD countercurrent flow is higher than delta T LMTD co-current flow. For sensible heat transfer between the two fluids, longitudinal fins are used in double pipe heat exchangers to increase the effective area of heat exchange. In fin tube heat exchanger, the corrosive fluid is generally placed in the shell side. Choose the correct statement among the following.
Option A, all of the above.
Actually the option 4 is incorrect. Like in fin tube heat exchanger, the corrosive fluid is placed in the shell side. Like it is incorrect, but all the other options are correct. 1, 2 and 3. Like the hairpin arrangement in double pipe exchanger accommodates larger heat length within the limited floor area. Also the uh, like LMTD of counter current flow is greater than co-current flow. For same inlet and outlet temperature, and the fluids for sensible heat transfer between the two fluids. But when there is a here it is a sensible heat transfer only, that is there is no phase change. So when there is a phase change, then the LMTD of both counter current and co-current will be same. But in like sensible heat transfer, the LMTD of counter current will be greater than co-current. Like and option C, uh, longitudinal fins are used in double pipe heat exchanger to increase the effective heat transfer area. Then option D is incorrect, because uh, generally the fouling and corrosive fluids are not placed in a shell side of the fin tube heat exchanger, because it can corrode the tube outer surface, which can lead to the damage of fin. So the correct answer is option B. All the three statements are correct, but option 4 is incorrect. Here we need to note that here it is given sensible heat transfer, but if there is no phase change, like if there is a phase change, then both will be same. LMTD of counter current and co-current will be same. Like question number 9, flooding in liquid extractor can occur by phase inversion due to high flow rate of dispersed phase, entrainment of dispersed phase droplet at high flow rate of continuous phase, presence of contaminants that can accumulate at the interface, all of the above. Like how flooding can happen in a liquid extractor.
Option D.
Option D. Option D is the correct answer. Then question number 10. A hot fluid is flowing through the inner pipe of length 4 meter of a double pipe heat exchanger with 3 hairpins to heat the cold fluid flowing through the annular region of concentric pipe. For a steady state heat transfer rate of 70 kilowatt and overall heat transfer coefficient of 300 watt per meter square Celsius, estimate the log mean temperature difference. The inner and outer diameter of the inner pipe are 54 mm, 54.5 mm and 60.3 mm. The inner and outer diameter of outer pipe are 82.4 mm and 88.9 mm. So can you see the whiteboard?
Yes, sir.
Like, can you see the question? Like, is it visible? Hello.
Yes, sir. Yes, sir.
Okay.
Visible.
Like here we are asked to find the uh, log mean temperature difference. The overall heat transfer coefficient is given. Overall heat transfer coefficient, like we know the relation between total heat transfer coefficient and total heat, which is if Q is the total heat supplied, then Q equal to uh, overall heat transfer coefficient U into area of heat exchanger into log mean temperature delta T m. Like here here it is a double pipe heat exchanger, so can you tell uh, for calculation of area which diameter should we consider, like inner diameter of outer diameter of inner pipe or outer diameter of outer pipe? Like let this be the inner tube with outer diameter of inner tube represented by d into DIO, and this be the outer pipe of the uh, double pipe heat exchanger, and let its diameter be DOO. So we need to, actually the heat transfer is taking place between the this surf this surface and this surface, like uh, the inner tube and the outer tube. So we need to take DIO, that is outer diameter of the inner pipe. Outer diameter of the inner pipe should be taken for calculation of area. So the area will be this 2 pi r into L, 2 pi into 2 pi into d0 into total length. Here they have told that 3 hairpins are there, so and the length of one pipe is 4 meter, so the total length will be 3 times 4, which is 4 meter, which is 12 meter. So on substituting this, we will get value of A as we obtained the area as 4.544. Next we need to find the LMTD from this values, like LMTD total heat transfer is given as 70 kilowatt. So the overall heat transfer coefficient U is given as 300 watt per meter square Kelvin. And the area is 4.544. Like on solving this, we will get delta T mean as. Okay, can you tell what answer you got here in degree Celsius? Hello.
I am calculating, sir.
Uh, like can you repeat it? I cannot get it.
I am calculating answer, sir.
Okay.
51.24.
Yes, 51.44. So here the main thing that we need to understand is that, like in a double pipe heat exchanger, we need to for considering the area of heat transfer, we need to use outer diameter of the inner pipe. That is DIO. Here they have given values of inner diameter of inner pipe, uh, and here inner diameter of outer pipe, but we need only the value of outer diameter of inner pipe, which will be considered for area of heat transfer calculation. And that when there are more than one hairpin in a double pipe heat exchanger, the total length is obtained by the product of number of hairpins times length of individual tube. So here we obtained 3 times 4, which is 12 meter. After that we calculated the area and we obtained it as 4.544. Then we can calculate the mean temperature, log mean temperature, which is Q by UA, which we got as 51.44 degrees Celsius. Okay, thank you for listening. Like, if you have any questions in this, can you please ask?
Sir, can you please repeat the question of pressure drop?
Question of pressure.
Allow, allow, yes, pressure drop, allowable pressure drop. How to select?
This one.
Yes, sir.
Like, actually, for a double pipe exchanger, the uh, like after calculation of pressure drop, for each exchanger there is a limit, allowable limit of pressure drop. So if we got the value of calculated pressure drop greater than allowable, then we can either uh, increase the diameter of the pipe. Like, if we increase the diameter of the pipe, we can reduce the fluid velocity by continuity equation, like A1 V1 equal to A2 V2. So on increasing the diameter, we can decrease the fluid velocity. So if we decrease the fluid velocity, we can decrease the pressure drop calculated. Like, this is the part of designing the pressure drop. So if we change the velocity little bit, then we can obtain a lower pressure drop comparable to the allowable limit. So one method is to select a larger pipe diameter. So if a larger pipe diameter is used, then velocity will be lower and the pressure drop will be lower. Like, also, if we can increase the length of the tube to increase the pressure drop. Also, we can place a fluid with higher flow rate through the higher cross sectional area. So if we pass a fluid with higher flow rate, then through a higher cross sectional area, then also the fluid velocity will decrease. So if the fluid velocity decrease, then pressure drop can be decreased. So this either a larger diameter or placing a fluid with higher flow rate through a higher cross sectional area can decrease the pressure drop. Like, is it clear now?
Sir, I have a doubt. If we increase the volumetric flow rate, there is a increase in the velocity. So how it is possible to reduce the pressure of?
Like, here they have told the along with increasing the volumetric flow rate on the side. like this I can tell in the next class about this one.
Okay, sir, no problem.
Okay, thank you.
Sir,
Huh.
I have also one problem related to heat transfer.
Huh.
Uh, Sir, I am working on a hydrodynamic cavitation. Uh, in this experiment, during the cavitation, uh, the temperature of water is increases up to 70 degrees Celsius, but I want to maintain this temperature at 35 degree Celsius. So what I will do, which type of a heat exchanger I will use, or
Like you
what are the.
like you need one uh, thermocouple and one controller, one temperature controller and one thermocouple to the system. So you need to
Okay,
set one controlled value, like you need to maintain it at 35 degrees Celsius. uh, like you told now, you need to maintain it at 37. Hello.
okay, yes, yes, I am listening.
So the thermocouple will measure the fluid velocity, and accordingly the heat will be produced. Like if we need to increase the heat, like if we need to increase the temperature, then the heating will be done on the surface. uh, so,
Okay,
so one thermocouple and one temperature controller is required.
okay. Thank you, sir.
Okay. Okay then. Thank you for listening.
Welcome.